In the name of Allah, the compassionate and the merciful. Hello guys, my name is Salar Delavar Ashqai, and in this video we're going to talk about the structural optimization. So in this example we're going to have a rebar diameter and column deep optimization of confined concrete section column with the two kind of analysis. First of all, nonlinear dynamic analysis, and the second analysis is pushover analysis. And our objective is to find the peak ground displacement must be less than or equal to demand displacement. So first of all, let's talk about the nonlinear dynamic analysis. So we run the analysis with the applied acceleration time history at the bottom of this column, and then outputting the displacement time history and finding the peak ground displacement. And then with the Newton-raphson method, this value must be less than or equal to the demand displacement. So, and in first analysis we want to find the best fitted rebar diameters, and in here our concrete properties, we use Mander relations for confined and unconfined sections, and also these relations for rebar diameter stress and stress relations, and also using 12 rebar diameters for our section with these confinement ratios, and then trying to fiber it in Opensees pi, and using Newton-raphson method for getting the best solution of finding of rebar diameters or even column deep. So you see at the end the optimization is going to be converged, for example in here 4 and 7 iterations. So let's back to the Opensees pi code. Guys, Opensees pi is very low speed and the Opensees is very high speed for running the code. You know, it's because of the Python efficiency is very low. So let's back to the Python code. I wrote Opensees for dynamic and pushover analysis. You see in here I defined the maximum absolute value to loading and reading the maximum value of the time history of displacement, and then in here I defined the function to read the dynamic analysis and run it. In here I defined the different layers of fiber concrete section for confined section, and also outputting the data. And let's see, in here we're going to have an optimization. So I defined these values as a length of column, height, depth of column, width of column, and also other values, rebar diameters. So in this example I used this value as a rebar diameters as the initial guess for our Newton-raphson first initial guess, and then with these values as a finite difference method for derivative converge tolerance and also converge tolerance, and these values trying to get the result with the target PGD, so is 25. So our example's target is 25. So let's back to the while cycle. You see, guys, I defined a while process, so the residual must be less than or equal to tolerance, and then in here we run the dynamic analysis, then outputting the maximum absolute value of the analysis. In here we read the file, and then minus the target function. So we define it as a f. So we defined derivative finite difference method for in this nonlinear solutions of Newton-raphson method. So I defined x minimum, so x minimum equals to x minus ESP, and then all the process as the same of the top, and then finding the f minimum, and also for f maximum is the same, and then in here we defined df is a finite difference derivative of f, and then defining the dx and residual, and then if the iterations not reach to the so the analysis is going to be stopped, and if it reached to the solutions, so optimum rebar diameters, it's going to be shown. If we run this code, you see that, for example, for 4 iterations, optimum rebar diameter is going to be calculated in here, and also the residual convergence is very low, so it gets the best solution. You know, this method is very efficient for modeling the different complex structural optimization when we defining the finite difference derivative method. Okay, guys, and let's back to the optimization of column dip. Yes, in here I defined this example. So in here our target is to find the optimum column dip of this analysis. So at the first initial guess it's equal to h call, and also all the process is the same, and you see if we run this code, it shows that after 4 iterations the optimum column dip is equals to this value. Okay, guys, so you see that it's very efficient for running and converging the different complex analysis. You see, guys, our convergence is depend on this value as a tolerance and ESP as epsilon finite difference derivative convergence. So the tolerance must be less than ESP. Okay, guys, if you change the value and you didn't get this result, so you must change these values or even increase these iterations and other, or even working for initial values for example guess of this analysis. So let's back to the pushover analysis. In pushover analysis all the functions is the same, but we defined in here as a pushover analysis. So you see the input values comes in here, and I defined maximum displacement for our our incremental displacement analysis, and you see I defined all the concrete properties is the same, and in here we're trying to output it, the values of the confined concrete section, and in here we define the maximum displacement and increased displacement for this in each step. So if we run this code and using this function, you see all the values is the same, and in this rebar diameter is first we are going to find the optimum rebar diameter. So the x is equals to dAB as a rebar diameter. So if we see that the code, all the process is the same as last analysis, but if we run this code, you see that after 4 iterations, the optimum rebar diameters based on this demand as a target displacement is going to be calculated. So it shows that the optimum rebar diameter is equal to 21, and it gets the good solutions for finding. And you know, this total time, it has just one cycle of analysis, not all process durations time. Okay guys, and let's back to the other solutions as a column dip optimization for this pushover analysis. You see in here our initial guess is a column dip, and our target displacement is equals to 8, and maximum displacement is equals to 10. If we run this code, you see that after 5 iterations, optimum diameters dip, optimum column dip equals to this value, and you see it gets the good solution. So if you want to change these values as a maximum pushover incremental displacement or even target displacement, so you get different results. So if you didn't get the converged solutions, so you must change these values. So the target displacements must be less than the maximum, because we push at the end of the analysis and then trying to find the optimum target displacement based on this pushover analysis. And so you see guys, we did the rebar and sectional concrete section optimization with the Newton-raphson method as a derivative finite difference method, and we get the good solutions for this convergence. And these videos, as I prepared for you for educational purpose. So guys, please have a comment and tell me know about this kind of analysis in my channel. Bye.